In 5.2, we'll be looking at factoring trinomials, specifically trinomials of the form x squared plus bx plus c. So this is known as a quadratic form. The idea here, though, there's two types of forms specifically we're going to see in this section. And for the first set of examples, notice the b and the c are places where numbers are going to go. There'll be a value here and a value here. But we didn't put what would have been a in front of x squared. The idea for these first problems is that we'll be looking at quadratic forms where the x squared term has just a 1 for a coefficient, and that's very important. So that being a 1 and nothing else is what allows us to use this approach we're going to look at. Now this approach, it's pretty straightforward once you know what the two rules are. This is something that when I teach it, I refer to this as the number game. The idea of finding two integers, so two numbers, p and q, such that they multiply p times q gives you c, but add p plus q to give you b. So two numbers that multiply to this and add to this. That's the thing we want to, the number game we want to play, right? So I'm going to refer to this as the number game, and specifically in these problems, you're going to hear me refer to this as the easy case number game. Now, the easy case number game is wholly dependent on this scenario, the fact that we're working with this trinomial in this form with a 1 coefficient on our x squared. Second half of this section, we will see the form ax squared, where there's a value out front, and although the number game will still be a part of the way we solve that problem, it is not this easy, right? I'll basically say this is the short and quick ones, the easier ones. That's why I call it the easy case. When we get to the other version in 5.2, there's a different name for that process, but it does incorporate the number game. Because notice, once we find these two numbers, p and q, that follow this number game, if they exist, we'll be able to take this trinomial and immediately break it down to the binomial of x plus the first one of the numbers and x plus the other number, to those two binomials there. And if no p and q exist to answer the number game, then it's prime. That polynomial can't be broken down. So, with that said, let's jump into a bunch of examples. So here we go. We got a squared plus 9a plus 20. We see the form. I usually refer to this as an x squared x no x form. A squared a no a in this case. But before we do any of this, recall from section 1, first step, G, C, F. Like I said, I'm going to write that for every single factoring problem we've got this chapter. So we ask this first. GCF of those three terms. Well, notice the A's are in those terms, but not this one. And if this is a 1, you don't have a GCF. You can't have a GCF of a number. So the GCF is just 1, and then we move on. So we've done that. We move on to this process. Now for this process, for the number game, the approach I like to use is start with the C. Start with the number at the end, the constant, and just think of the different pairs that multiply to 20. And I always use an organized approach. I start with 1 and the number, and then I just start counting up from 1, asking does that number pair with something to give me 20? Meaning after 1 comes 2, and I know 2 and 10 give me 20. After 2 comes 3, 3 is not a factor of 20. After 3 comes 4 and 5 are factors of 20. But you don't need to do this very long, because as this list of numbers goes up, this list definitely goes down. And notice, I don't even need to go beyond 4, because if I asked about 5, it's right there. So as this list goes up and this list goes down, they eventually meet, and you're done even worrying about factors. So a good organized approach makes that not take very long. So now, with those three sets of numbers, the question is, do any of those pairs of numbers multiply to, and keep in mind the signs, multiply to a positive 20, but also add to a positive 9? Well, clearly that pair right there. Also add to 9. So that's our, they call it P and Q, that's our numbers for a number game. And there is no algebra work here. We just take this trinomial and we say that it factors into two binomials, each of which start with an A. And then since it's positive 4 and positive 5, it's plus 4 and plus 5. And there's your answer. Now I want to go ahead and point out, like I mentioned in the last video, with factoring you can check. And with this number game, it's not a bad idea to take the time to make sure you chose the right numbers and the right signs. So you can always check. I'll go ahead and do this one check here. And take a plus 4 and a plus 5 and do the multiplications. So we get a squared plus 5a and then plus 4a plus 20. And I like doing one check on this one just to really show you exactly why this number game worked the way it did. Because notice we've got a squared, and if you combine your two a terms, you get 9a and 20. That's what we started with. But notice this is why the number game works. Because the two numbers you put here are going to be combined by this arc right here to give you that number 20, the final number, the c that they need to multiply to. And those two numbers are going to be coefficients on these two arcs for your a terms that are going to add together to give you that middle term. So that's why the number game has to work. That's why these two numbers have to follow those rules so that this will all play out. All right, let's look at some more examples on the next page. All right, we need to factor. So, first step, GCF. I know, I heard you say it. I'll pretend I did. So, GCF of those three terms is a 1, right? Nothing in common, so moving on. We see the pattern of a b squared b constant, right? b squared b, no b. So, we go off to the number game, because this is a 1 out front, easy case. So, start with 10. The only factors of 10 are 1 and 10 and 2 and 5. Now, we need these numbers to be numbers that multiply to a positive 10, but also add to a negative 7. So, I mentioned sign is always important. If you're multiplying to a positive value, they're either both positive or both negative. And in this case, if we're trying to add to a negative number, it wouldn't even make sense to think about positive numbers being an answer. So we'll just go ahead and say, what if it was negative 1 and negative 10, or negative 2 and negative 5, and then we realize that, yep, that pair right there would be a pair of numbers that both multiply to a positive 10 and add to a negative 7. So we get to our binomials that start with b this time for a variable, minus 2, minus 5, and done. All right, example 3. First step, GCF. 3 terms, nothing in common, GCF is a 1. Okay, so now we look at the constant term of negative 5. I want numbers that multiply to negative 5. Well, that would just be 1 and 5. Now it's a negative 5, so it could be a positive 1 and a negative 5, or a negative 1 and a positive 5, right? Either of those is an option. However, do either of those add to positive 3? No, they don't. These are our only options. If we're going to use the number game, it's got to follow the rules, and there aren't any that follow the rules. So, as it said on the previous page, if that's the scenario, then that polynomial is prime. We weren't able to factor out anything with a GCF, and the number game didn't work for us. So, this would be a prime polynomial. Okay, let's look at a couple more. So, got a factor. First up, GCF. Now we've got some p's in common there, some q's in common there, but nothing in common between all of them. So GCF is 1. Now the thing about this is it looks a little different because I can't really call this a p squared p no p, although notice I kind of can. If you're looking at the p variable, there's p squared there, there's p there, and there are no p's here. So this particular polynomial with these other variables, specifically q in here, notice that q follows a very specific pattern going to the left of q squared, q, and no q. With that pattern existing in both directions, this ends up being a trinomial that does fit the pattern of what we've been factoring. So if this had just been a random q in there, we'd have an issue. If there's just a random variable in there we couldn't account for, we could not factor this. But because we have that pattern of q squared, q, no q going backwards, we're going to see how this does absolutely fit the form that we've been working with. So it's an easy case, right? 1 out front, so that's good. And so we'll go ahead and use our number game with that negative 6. Just focus on the number. So numbers that multiply to a 6 are 1 and 6 and 2 and 3. Now, we need them to multiply to a negative 6, add to a negative 5. This is one, and there's ones like this, where you want to really be careful and take your time, because both of these numbers, both of these pairs of numbers, excuse me, look like we could get them to give us a negative 5. We just need to make sure we pick the right numbers with the right signs that follow both rules. Keep in mind, if they multiply to a negative 6, then we have to have one of each sign. So I'm going to go ahead and just write those options out. Positive 1, negative 6, and, negative 1, positive 6, and positive 1, negative 6. Negative 2, positive 3, and positive 2, negative 3. So one of those four pairs is our only option. And if we needed to add to a negative 5, then specifically, it's got to be that pair. So take your time on these, especially in these scenarios where there might be more than one possible pair that looks convincing. And what I mean by looks convincing is I've had a lot of people tell me the numbers, the P and the, well, this is a bad example, but the two numbers for the number game are negative 2 and negative 3 because they added negative 5. And people overlook or just miss that negative 2 times negative 3 would not give you a negative 6. So that's got to be the numbers and their signs. Now, when we go to break this down, it was a p squared p no p, so it makes sense that we will start both binomials with a p. We found our numbers of plus 1 and minus 6. So plus 1 and minus 6. Turns out, to get this q squared q no q pattern going backwards, those two terms simply need to be q terms. If you allow each of those to be a q term and you were to check this and distribute all this out, you will get that exact pattern, and that will always work. So no real difference in the number game here for this weirder pattern. Just make sure we append those q's there on those second terms. Okay, and this one should be our last example. Yep. So we need to factor. First step, GCF. And for the first time here, GCF is something other than a 1. Not only for the numbers 3, 12, and negative 15 do those have a 3 in common, but notice the a's. We got a cubed, a squared, and a. There's an a that is found in each of those terms. And that will be very useful, very, very important actually. Let's factor that out first and see why. Factoring out the 3a, so the 3 is gone and one of the a's is removed, so we're down to a squared. Now 3a times what to give me 12a squared would be a plus 4 and one additional a. And then 3a times a minus 5 to give me minus 15a. Notice this GCF and both parts of it are critical that we found them, because without them, if we hadn't found that a, first of all, this wouldn't even be an a squared a no a, right? If we did not factor that out, notice that's what we're left with here, is an a squared a no a. But we couldn't have done anything with this if we did not find that a GCF. And the 3 specifically, being in common with all those terms, if we had not factored out that 3, then this a squared term would still have a 3 in front of it, and this easy case number game we're using would not apply. The method we're about to learn in the next set of notes would actually be the thing we need to use if there were a number out front here. But this 3 and a, reduce this down. Now here's the deal. Just because we find a GCF does not mean we're done. We just do that first. Now we work with what's left here. Being an a squared a no a, easy case. I'll go off and do the number game off to the side here. Numbers that multiply to a negative 5, so it'd be the numbers 1 and 5. And if I need them to add to a positive 4, we would need a negative 1 and a positive 5. So back to the problem. The 3a GCF just sits there while we take this trinomial, and break it down to two binomials that start with a's, and then we fill in our number game of minus 1 plus 5. And there's our fully factored final answer.